Okay, let's get started with our next hazard analysis. This is going to be analysis number 8. We're going to go to our database and let's load in our database. Come up here to the menu, we go to add-ins, EasyHas PDB, load PDB from file. And we know that it's in our course examples, .pdb, that's the extension we're looking for. This is our database. So we load it in. We stopped with analysis number 7. So we want to go to 8. That is record number 9. Let's highlight this record. Go to add-ins, EasyHas, load parameters from PDB record. So we have these parameters in. Now these are the parameters from a 10-watt Vanadate. We see this type of laser in laboratories often, particularly pumping TISAF lasers. 532 visible wavelength, 10 watts. Exposure duration is 1/4 of a second. That's our ANSI default based on our aversion response. Let's take a look at the MPE. This is one we recognize. It's 2.55 milliwatts per square centimeter, which is our standard MPE for a 1/4 second continuous wave visible laser. Our skin MPE, considerably less restrictive, 3.11 watts per square centimeter, but it's still 33 times, this particular laser is 33 times the skin MPE. 10-watt green laser is going to hurt if you stick your hand in it, but it will be a self-correcting action. You probably won't do it again. The beam information we have is the beam diameter. This is a circular Gaussian beam at the 1/e² points, 1.5 millimeter diameter, 1/2 milliradian divergence. Nice laser. 1.1 is m², which we'll talk about in just a little bit. Observer range default is about 1/2 meter. That's, we figure, we sort of look at this as the waist is going to be close to the aperture, and in the ANSI equations they're assuming the waist is at the aperture. That's not always the case. So really what this means, observer range, it means that you are 1/2 meter away from the beam waist. We can go ahead and sort of think about this as being at the aperture, close to it. So we're 1/2 meter away from the smallest point in our beam. You can tell that because the beam has grown just a little bit over 1/2 meter distance over the 1.5 that we originally put in. This is the diameter of the beam at the observer range. So if we crank this observer range up to, say, 10 meters, we'll see a significant change in the beam diameter. So I'm going to put this at 0 for right now. All right. OD at observer range and, of course, worst case are identical. This is because the beam diameter at 1.5 millimeters through a 7 millimeter limiting aperture, we get 100% transmission through the limiting aperture. So the OD observer range and worst case will be the same, which is 4.009. Now the question we have for our OD value is, what do we buy? Do we round this up to 5? In this case, no. We'll stay at 4. Remember, this needs to be 4.1 or above for us to round to 5. So from 4.1 to 4.99, we'll go to 5. But if we're under 4.1, we'll round down to the nearest whole OD, which is in this case 4. And it's perfectly acceptable because there's plenty of cushion built into the tables that we're really reading from to calculate our MPE and eventually getting our results here. Next thing I'd like to look at is the NOHD, 2,000 meters. Let's quickly check the skin hazard distance, the nominal skin hazard distance. Okay, 56.7 meters. That's because the MPEs are different, right? Okay. So this is about right for the skin NOHD. 56 meters is a hazard distance, 33 times the skin MPE. If we're right near the waist of the beam, this looks all about right. Let's switch back to our NOHD. Something I want to talk about, what really affects an NOHD? What really causes it to either get longer or shorter? Well, it's beam divergence. Let's look at this for just a second. And let's reduce the beam diameter, beam divergence by 0.4. So we'll have 1.5 and we'll go to 0.4. What this does is this tells us we're trying to exceed a theoretical limit. Okay, I'm going to say OK, and when it does, it's going to change the divergence to the lowest possible divergence that it can. Right. So 4.5 is the lowest divergence that this wavelength with this beam diameter can achieve. We're going to look at m squared and how beam diameter and divergence are really related to each other in just a little bit. But for now, we'll notice that we changed the beam divergence by just a half a milliradian. Actually, only 0.05 milliradians. And we'll notice that we added on almost 200 meters to the NOHD. What happens if instead of 0.5, which is our original divergence, we double it? Well, it's going to make sense. If we double the divergence, we go from 0.5 to 1. The NOHD doubles, or I'm sorry, gets cut in half. Why? The divergence is bigger. So this beam is growing faster, which means the irradiance is going down. So the NOHD will get shorter. What happens if we double the divergence again? Let's go to 2. Yeah, of course, it gets cut in half to 500 meters. This is important to understand that divergence has much more to do with NOHD than diameter. Let's go back to our original conditions, 1.5 millimeter beam diameter and 0.5 milliradian divergence. This is got back our standard, our beginning NOHD, which is 2,000 meters. Let's change the beam diameter, and let's make a significant. Let's change it by a factor of 10. So let's go to 15 millimeters and 0.5 milliradians. Yeah, no change in the NOHD. Well, let's do it again. Let's increase the diameter by a factor of 10. We'll go to 150 millimeters, and we'll go to a divergence of 0.5. We'll notice, yeah, you get a slight difference. So you can see that changing the diameter of the beam doesn't have much of an effect on the NOHD when compared to the divergence. So it's the divergence that really affects the NOHD here. Okay? All right. I think everything else is pretty explanatory. One thing I might want to point out, notice that you have two different time scales here. All right. If you're looking at the slide and it has a different point source NHC than 0.564, it's because of the exposure duration. Let's change this exposure duration to 1/4 of a second, and you'll notice that, yep, this is the NOHD that you're seeing in your book. Right? So it's a time difference thing. For diffuse reflections, we like to default to 600 seconds, okay, which will give us a slightly larger NHC for the diffuse reflection than what you're seeing in the book. All right, I think that's about it. We'll move on to the next analysis.